So the first thing we're going to do is we're going to call this function weak learn. Generate a rough rule of thumb. Generate an imprecise classifier, something that is roughly correct. You can use whatever you like. And we're passing into it our x's, but more importantly, the distribution of weights, because the weak learner is going to use the weights to actually induce decision boundary. What it returns to us is something that is formally defined as H. H stands for hypothesis. It's a weak classifier. Capital H, this one here, is your strong classifier. It's the whole ensemble, right? So the big H is made up of little h's. And the little h is going to have the decision boundary, or some definition of what your classifier is and how it's classifying. In our case, we'll talk about the decision start. We'll have a direction, number 2, and it will have an error term associated with it, which is being calculated here in the algorithm in the next step. So, the algorithm has gone through all the possible boundaries, decision boundaries that it could generate, and it has chosen this one as being the most optimal. Now what we need to do is we need to determine what is the weighted error rate of that particular H, of that particular weak classifier that was generated. This is how we do it. It actually needs a 1 minus this sum term, I've noticed just today actually. What we're doing is we're summing up the weights of all the samples, like this one and this one and this one, this one that were misclassified. So we're looking for the weighted error, not the absolute error, the weighted error, and that goes into this. Then what we need to do is we need to assign a level of competence to this H. How good is this weak classifier? So the way we're going to determine its competence is by generating an alpha value, which you will see when you see alpha, you think competence or confidence level of that weak classifier. The way we do it is using this expression here. So we go 1 minus the weighted error divided by the error, the weighted error, and we apply the natural logarithm to it times it by half. I'll show you what that function looks like in a second. So now we know how competent this is. Based on this competence, we now need to change the weightings of the data set. Because I said before, well, we need to increase the weights of samples that have been misclassified and reduce the weights of those that were correctly classified. Well, by how much? Do you do it uniformly? Well, you shouldn't. You should do it in proportion to the confidence you had in that classifier. If your classifier was fairly rubbish in the previous round, well, you shouldn't just absolutely change the weights around of all the samples. You should change them around a little bit. But if your classifier was really, really good and a sample was misclassified, that means that sample is really, really hard to learn. Let's boost up its weight for the next round proportionally to the competence of the previous classifier that was unable to classify correctly. That's what's happening here. So in this for loop, we now go through each one of these samples, and we're checking to see was it correctly classified or incorrectly classified, and depending on the result, we boost it up or reduce it down. H, parentheses, is a function, right? A classifier is a function. What does it return? Given this problem, what does H return when we apply it to a sample, given this problem domain? What would it return? Yep, and what's the classification? What are the options?
-1.
-1 or 1. All right, so let's look at this. So we've got minus alpha t, y label, I, h, t applied to x. So this term returns -1 or 1. Let's say returns 1. So 1 times the label of this, let's say it was a positive sample, so it was correctly classified. So 1 times 1 is 1. Then we times it by the competence of the classifier, which could be any number. I'll show you what that looks like. And then we times it by minus, because it was correctly classified. So we'll see that in this function, this exponential function, anything below 1 will start giving you a fraction. And so what we want to do is reduce the future weight of that sample that was correctly classified. And likewise, for the sample that was incorrectly classified, we want to amplify it. So if the sample was classified as -1, but it is a negative sample, so -1 minus -1 is, what am I trying to say? Let's say it's the same sample, classified as negative, but it is a positive. So this ends up being a positive result. Times it by negative, so it's a neg. Hang on a second. We got x. Let's say x equals 1. X equals 1. In terms of its label, this is its true label. Let's say h x equals -1, and let's say. And then we have -1, which is associated with the alpha value. So we have 1 with this, which means it's a misclassification that we want to boost it up. That's how it's kind of working. Once we have adjusted the distribution of weights for each one of the samples, all this does here is normalize everything. It just normalizes all the weights, and then it does the same thing again. Now let's have a look at the distribution of alpha values. So remember the function for generating the alpha value? It's half times the natural logarithm of 1 minus the weighted error divided by the weighted error. So that produces this kind of a function. So as the training error increases, and remember, I'm not sure if I said it, but we don't accept, or we classify whose training error is 50% or above. The training error has to be just better than chance. So up to, but not including 0.5. So this, in essence, shows how the competence of the classifier decreases as the training error increases. As the training error of the particular round gets smaller and smaller, the alpha value shoots up. Right, so that's how we assign the competence value of alpha. Now this is the weight update function of each sample. So given the alpha values previously, remember this is now going to be alpha value that we punch in. This is the value that we punch into the exponential function if the sample has been correctly classified. It's a negative, remember, because we want to reduce its weight. And what happens is, up until 1, we generate a fraction, which means that the original weight is going to get smaller and smaller and smaller, and likewise above this point here it starts to increase. Okay, so that's a function that is applied to essentially changing a data set by changing the weights of each one of the samples. And once we're done, once we have our classifier, what we do is we sum up the H term, which is the weak classifier, every weak classifier applied to the sample X, which remember returns -1 or 1, we times it by the alpha, the confidence of H at that iteration T, and we sum up all the alphas essentially, because this is just returning a sign, -1 or +1. And what we do is we take the sign of that final sum. If the sum is positive, then the classification is positive. If the sum is negative, then the classification is negative. And that's the final classification for X when we apply the strong classifier. We'll talk about what those sums mean, and we'll study them in detail next week. But for now, the actual classification is really, really simple. We're just looking at the sign. Here's the final result, negative or positive. Here's your answer. It's as easy as that. Isn't it beautiful though? You've got to say. Even though I'm sure that you haven't quite grasped this takes quite a while to sort of fully digest. You have to appreciate the beauty of the idea. It's phenomenal. So let me give you an example.